SASE architectures, are facing some unprecedented challenges from quantum computing threats, mainly because of their cloud-native design and their dependence on those traditional cryptographic protocols that quantum computers can, efficiently break. Right now, most SASE implementations rely pretty heavily on RSA and elliptic curve cryptography to set up secure tunnels, authenticate users, and protect data as it moves between all those distributed endpoints and cloud services. And here's the thing, the convergence of networking and security functions within a single cloud-based platform actually creates these concentrated attack surfaces where quantum adversaries could potentially compromise an entire organization's security infrastructure through targeted cryptographic attacks. The hybrid nature of modern SASE solutions, exemplified by Check Point Quantum SASE, which combines on-device and cloud-based protections, introduces additional quantum vulnerabilities across multiple attack vectors. While these architectures provide enhanced performance through direct internet access and reduced latency, they also multiply the cryptographic dependencies that quantum computers can exploit. Each component within the SASE stack, from zero trust network access to cloud access security brokers, relies on cryptographic primitives vulnerable to Shor's algorithm, creating cascading failure scenarios where compromise of core cryptographic functions could render entire SASE deployments ineffective. SASE's distributed architecture particularly amplifies harvest now, decrypt later vulnerabilities as encrypted traffic flows through multiple cloud points of presence that adversaries can monitor and collect systematically. The global nature of SASE deployments means that encrypted communications traverse international boundaries and potentially hostile network infrastructures, where nation-state actors can implement large-scale data collection operations targeting future quantum decryptions. The geographic distribution of sensitive data across cloud providers creates persistent exposure risks that extend far beyond traditional perimeter-based security models. Current SASE security frameworks offer no inherent protection against quantum threats because they primarily focus on integrating existing cybersecurity technologies rather than introducing quantum-resistant innovations. The consolidation of multiple security functions into unified platforms means that quantum compromise of underlying cryptographic systems can simultaneously disable firewall secure web gateways and access control mechanisms, creating complete security infrastructure failures rather than isolated vulnerabilities. The emphasis of the SASE ecosystem on real-time policy enforcement and dynamic security controls requires frequent cryptographic operations for continuous authentication and authorization decisions. These high-frequency cryptographic interactions generate substantial volumes of encrypted traffic that quantum adversaries can collect and analyze. In contrast, the distributed processing requirements may limit the feasibility of implementing computationally intensive post-quantum algorithms without significant performance degradation. Organizations deploying SASE solutions must prioritize crypto agility frameworks that enable rapid migration to post-quantum cryptographic standards once they become available. And the centralized management capabilities inherent in SASE architectures could facilitate faster cryptographic transitions compared to traditional distributed security deployments, provided vendors incorporate algorithm flexibility into their platform designs from the outset rather than retrofitting quantum resistance as an afterthought.